Hello, everybody, and welcome to a new virtual tour of ESO's Paranal Observatory. My name is Hector Salas, and together with Farid Char, we will be your guides today. So, allow me to introduce myself. I'm a PhD student at the Leibniz Institute for Astrophysics in Germany, and I have been a part of the team of guides for Paranal Observatory since 2019, back then when I was living in Antofagasta and doing my master's there. I work mostly with topics related to the circumgalactic medium, that is the environment that surrounds galaxies. And I will be your guide today. And Farid, he will be your producer today. Farid, how are you?
Hello, Hector. Good morning. Um, yeah, I will be your producer today. In my case, I have been a tour guide of the Paranal Observatory for more than 10 years, and I have some experience in astronomy outreach and education. I have been working for an astronomy center in the University of Antofagasta. So yeah, we are going to be your guides for this virtual experience, and we are going to take all your questions. So I will be in charge of taking questions and um, uh, let's say answering during some specific moments of this tour. So I ask you to all our virtual visitors to send your questions or comments to answer them during this virtual experience. So let's go, Hector. Let's go ahead with this tour. Thank you.
Okay, well, as Farid mentioned, you can leave all your comments, your greetings, your questions in the chat, either in Facebook or YouTube. And we have some times to answer them. Okay, so let's start. And the first thing we want to talk to you about is about ESO, the European Southern Observatory. So this is an international organization that is comprised of 16 countries. And we have an image to show them on that is right there. So you can see we have Denmark, Netherlands, United Kingdom, Ireland, Belgium, France, Portugal, Spain, Sweden, Finland, Germany, Poland, the Czech Republic, Austria, Switzerland, Italy. And we also have two non-European countries. We have Australia, that joined recently as a strategic partner, and we also have Chile. Chile is the host country. The telescope that's controlled ESO, they're all in Chile. Now, ESO started in the 1960s. They wanted to build new facilities to develop the scientific investigations in astronomy and also to promote them to the outreach to community. And at the same time, Chile was trying to attract human capital to the country to develop the scientific potential that they have in the northern skies. So they come to an agreement, and Chile offered land, and ESO start building the facility there. And we have three different sites of observation of ESO in Chile. We can see them in the next image of the screen. Farid, can we show the three sites of observation
Yes,
for?
Hector, give me a moment, please.
Okay,
Okay.
there. Thank you. There we are. So the first one was La Silla Observatory. He was inaugurated around 1969, if I'm not mistaken. But that could be maybe you can correct me, Farid, if I'm mistaken. The main telescope there is
Yeah,
the
it's
is
inaugurated
yeah, correct me.
in 1962.
62. Okay, thank you. So the main telescope there is the ESO 3.6-meter telescope that is equipped with a very special instrument called HARP that is specialized in detect exoplanets. We also have there the NTT, the New Technology Telescope. Farther north, in the region of Changnator, we have both ABEX and ALMA. These are both radio antennas. And in the case of ALMA, this is not just ESO. This is an international collaboration with ESO, the US, and some countries from Asia Pacific. So ESO is a partner in this observatory. And in the same region, but toward the coast, we have Paranal and Armazones. So Paranal is the place we're going to visit today. And there we have the VLT, the Very Large Telescope, and VLTI, the Very Large Telescope Interferometry Mode. We also have the VST and VISTA telescopes. These are survey telescopes. So they map the whole sky. And very close to Paranal Mountain, we have the Armazones Mountain, where the ELT, the extremely large telescope, is currently being built. It's very close. Actually, the ELT is going to be controlled from Paranal Observatory. And in the region between Paranal and Armazones, the CTA South is being built. This is an array of radio telescope that is specialized in detecting gamma rays. So, okay, so now we have an idea of the different observational facilities of ESO in Chile. So we're now going to travel virtually to Paranal. I'll mention to you that the mission of ESO is to build, design and build instruments for the astronomical observations, to control the observatory size, and to promote the collaboration within different science and the outreach of this astronomical science to the public. So here we're traveling virtually to the Atacama Desert, the driest desert in the world. We are at about 1600 kilometers north of Santiago, the capital of Chile, and about 130 kilometers south of Antofagasta, the regional capital. The closest city is Taltal, that is at about 90 kilometers to the south. Then in the background, we see Paranal Mountain, that reaches heights of 2,600 meters above the sea level. And here we're actually very close to the coast. We are at 12 kilometers from the ocean in a straight line. So maybe you're wondering, can we see the ocean in this video? And well, if you look there in the background, there is a hazy part. Those are a bunch of clouds that are covering the Pacific Ocean. So why do we have clouds in a place that is dedicated to astronomy? Well, this is because of the influence of the Humboldt current. So this is a current of very cold water that comes from the Antarctic and goes through the coast of Chile and Peru, and it produces an effect known as thermic inversion. And basically what this does is that all the humidity concentrates below 1,000 meters, and all the clouds are formed at that altitude. So since here we're about 2,600 meters, we're above the clouds. So all the very humid air that is not very good for the astronomical observation is below us. And here we also have another natural barrier that makes this site excellent for astronomical observations. About 200 kilometers towards the east, we have the Andes. And at this place, the Andes, they reach very high altitudes, and they stop the clouds and the bad weather coming from Argentina and Bolivia. At this place, the Andes is over 6,000 meters in height. So this gives us an idea of why do we have these amazing conditions here for astronomy. But let's go a little closer to the top of the mountain, shall we? And we have a video showing it close up. Here we have. So here you can see the different telescopes and their names. And as you can see, the top of the mountain has been cut, arrows have been built, and we have everything that we need to do the observations. I also would like to comment you that the name Paranal in the language Quechua means whirlwind, and this could be a reference to the whirlpools that sometimes forms in the desert. But usually the air here is very calm. We have over 300 nights, clear nights during the year. So we are going to move and we're going to put ourselves on the main platform of Paranal Observatory. So here we are in the main platform, and let's just take a look around first. Over here we can see the clouds. Below the clouds we have the Pacific Ocean, and now we're starting to look towards the south and we see this beautiful desert landscape. Over here is the base camp, and over here we have Volcano Yuyayaco. This is the border with Argentina. Chile is a very narrow country, and this is actually one of the widest parts of the country. And here is the site of Armazones, where the ELT is being built. Okay, so the big star telescope of Paranal Observatory is the VLT, the Very Large Telescope. But this is not a single telescope, it's an array of these four big telescopes that we can see on the screen. So we have UT1, UT2, UTT3, and UT4, where UT is for Unit Telescope. Each of them has a primary mirror that is 8.2 meters in diameter. Additionally, We have some smaller telescopes, the auxiliary telescopes or AT. We have one over here, second one over here, a third one, and a fourth one. They have a primary mirror that is 1.8 meters in diameter, so about the size of a tall person, let's say. And these telescopes, they're very special. As you can see, they are on top of tracks, and this is because they can move. And they can move because these telescopes, they work using a technique called interferometry. And you see these little trapdoors over here. There are about 30 of those in the platform, and we can put them in any of those 30 positions. And to tell you about interferometry, we have a small video that helps us to explain this. So when you are doing interferometry, what you're doing, you are combining the lights of different telescopes that are observing the same object. And in this case, this is not done digitally with some post-processing software. This is done in an analog way. The light is sent through underground tunnels into the central building that you see in the image, that is the interferometry building. And here, one of the things that matters is what we call the baseline. This is the maximum separation between the telescopes. When we are using the four small telescopes, we can reach a maximum separation of about 200 meters. And to simplify this gives us a resolution similar of a single telescope that is 200 meters in diameter. So we're creating a virtual mirror of 200 meters. So if this technique is so great, why don't we use it all the time? Why are we still building larger and larger telescopes? Well, we increase our resolution, and this is the ability to differentiate two things in the sky. So if two stars are too close together, with low resolution, they might look as a single star. With a high resolution, we can see them as two different objects. But what we don't increase is how much farther away we can see. Objects look dimmer either because they are intrinsically dimmer or because they are farther away. And if we want to see objects that are less brighter, we need to collect more light. This is like putting a bucket on the rain. The larger your bucket, the more rain you collect. The larger your mirror, the more light you can collect, and therefore you can see less bright objects. Okay, so the four big telescopes, they are essentially the same on the inside, but they have one major difference is that they have different instruments. Each one of them has a space for three instruments or three cameras if you want. Now, we don't have time to go into all of them. We're only going to enter one of them. We're going to go into UT3. But before we go inside, I would also like to comment that the telescope were given names in the Mapudungun language. This is the language of the Mapuche, the natives from the central and southern parts of Chile. And in that language, we have UT1 is Antu, and Antu means the sun. We have Cuyen, which means the moon. Then we have Melipal, and Melipal means something like four stars, and is essentially a reference to the Southern Cross constellation. And then we have Jepun, which is a reference to the planet Venus and means something like the evening star. Now we are going to go to Melipal. So here we are inside the telescope, and let's just first start by looking around. So we see here some people working during the day, doing some maintenance, and they help us give an idea of how big this is. Here we are in what would be the fourth floor of the telescope. This is very big. Here we can see the primary mirror. This is made out of a single piece. There are larger telescopes, but they use segmented mirrors. This is a single monolithic mirror made out of a special material called zero dur. This is a mix of glass and ceramic and is 8.2 meters in diameter, but only 70 centimeters thick. In addition to the primary mirror, we also have a secondary mirror here on the top, and we have a third mirror that we cannot see very well on this image, but is somewhere here at the center. Now, this telescope has two motions. The blue part, this is the mount of the telescope, is fixed, and this part can tilt. That's one of the motions. And for the second one, as you can see, this part of the floor is separated from the rest. That is because this part here can rotate in 360 degrees. So combining this rotation with the inclination of the mirror, we can point at any place in the sky. Now, let's go downstairs a little bit. Here we are below the mirror, and here we can see the cell that supports the mirror. The mirror plus these white cells, they weigh at about 22 tons. And here we have these little gray boxes. These are the actuators. These are part of the active optics technology. So what do they do? Well, this zero dur material, it has a little bit of a flexibility. So when you tilt the mirror, it flexes a little bit because of its own weight, because of gravity. And this is important. If this material was not flexible, if we were to use the same kind of glass that you use for the mirror at your house, the mirror would just break because the stress is too high. So the solution was to use a slightly flexible material. But this means that the curve of the mirror is going to change. To correct that, here are the actuators. So we are actively measuring the curvature of the mirror in real time, and we're correcting it. These little actuators, they're like pistons. They can push or pull, and they ensure that the curve of the mirror is always the same, so that we always have the same quality of observations. And well, let's go back up. So how does this work at night? Well, first we must open the enclosure, and this part over here with a chip of bell opens, and we have a small video showing this better. The video is a simulation that is obviously exaggerated. The enclosure doesn't float on the air, but you get the idea that it's open so we can let the light go through. The light is going to come from the sky, hits the primary mirror, going to bounce into the secondary mirror, and then bounce again to the third mirror. And the third mirror is in charge of directing it either to the instrument on the right or to the instrument of the left, or we can just let the light go through to the instrument that is below the telescope. So that way we can choose each of the which instruments we're going to use, which here are represented with the red, blue, and green box at the bottom. Okay, so we can go back here to the telescope, and here we can see one of the instruments is here. In this case, it's called BIMOS. The other one is on the other side of the screen, and the other one is below here. Now, I think we have some time to maybe answer some questions. Do we have any questions or comment, Farid?
Uh, Hello, Hector. Well, no, right now we don't have any questions. We have some greetings. That's why Graven from Amsterdam, the
Mhm.
Netherlands. But we don't have any questions so far. Maybe I can ask you a question for now. One of the typical questions during a tour in Paranal. What is necessary to do for maintenance for these mirrors? Because, well, I think the mirror is the most important part of the telescope. So, what can you tell us about the maintenance? How we can clean the mirrors?
Yeah, so maintenance of the mirrors is important because yeah, dust and other particles can deposit on the surface of the mirror, and then the quality of the observations degrades over time. So we need to take care of this, and there are two ways that we handle this. So for one of the methods, an engineer or will use this lift over here, and we will tilt the mirror, and the engineer will spray it with a foam of carbon dioxide. This foam will come down because of gravity, and it will drag any dust particles that is settled on the surface of the mirror. And this is done every other week. It's a relatively simple process. There is a second maintenance that is slightly more complicated. For that one, we remove the mirror plus this white cell, and to do that, we use these yellow leaves that we have over here outside. The mirror is then put into a special truck, and taken to base camp to a special building. There, we remove the layer that gives the reflectivity to the mirror. This is a layer of aluminum that is nanometers in thickness. So this layer gets removed, and then in a different building, a new aluminum layer is placed on the mirror. This whole process takes about a week. During that week, there is no mirror in the telescope and it can be used. And they have to be very careful because there are no replacements for these mirrors. So if anything were to go back in the whole process of moving the mirror, removing the aluminum layer and bring it back, that would mean that we would lose one of the four big telescopes. So this is a very delicate process. And this is done every 18 months, but it's done in sequence. So if today is for UT1, 18 months later will be the turn of UT2, and so on and so on. So two of the two different maintenance methods that we have. Simple cleaning and the realuminization process or recoating process. Okay.
Okay, Hector. Thank you very much. We don't have more questions. Well, we have a reading from Andrei Popov. Happy New Year. Well, Happy New Year for you and for everyone.
Yeah.
Um, but I hope the people can send your questions or comments because we are going to answer. We are going to try to answer all your questions in this virtual experience. So please don't forget to use the comment box in Facebook or YouTube, and we will try to answer your questions in another stop for this visit. So, okay, Hector, thank you very much, and I think we can continue now.
Okay, thank you for it. Okay, at night there cannot be nobody inside of the telescope. So maybe everybody has seen this image of the astronomer looking through the eye of the telescope. That is a very romantic notion that is no longer truth. So during at night there is nobody inside here. Everything is being controlled from the control room. And the control room is over here. So and that is our next stop in the tour. So here we're seeing the control building from the side. Here, in addition to the control stations for the different telescopes, we also have some offices for the engineers and people working here. So we're going to be inside here. I have here different sections to control the different telescopes. As you can see here, there is a sign saying UT4. This whole area over here is just to control the UT4 telescope. Over here, we have for the UT3 for Melipal, where we're just visiting. As we advance to this room, we see the space for the UT1 and for UT2. And we're going to stay inside this part over here. And as you can see, there are a lot of screens, so maybe that's what calls the attention the most. The amount of computers and screens that you can see in this image. So why do we have that many computers? And how many people does actually are necessary to control a single telescope? Well, at night, during the observations, there are only going to be two people here. There's going to be an astronomer and a telescope operator. So these telescopes, they are very high technology and very expensive, so they don't trust astronomers to control them. There is a specific job that is the job of the telescope operator. They control and handle the telescopes. You can think of it as a pilot and a co-pilot in a plane or in a rally car. The pilot, the telescope operator, he is controlling the machine. He is in charge that everything moves the way that needs to be moved and everything works correctly. The astronomer, he's the co-pilot. He has the map, the route that we're taking place, and he's in charge of controlling the science that is being done. Okay, if only two people are here at night, well, why so many screens? Why so many computers? Well, you have to remember, each telescope has three different instruments. So we are going to want to have a dedicated computer for each one of them. We're also going to need screens giving you information about the weather conditions. If the weather conditions are not good, we may need to close down. And sometimes the problem here is the wind speed. If the wind speed is too high, a small pebble could be lifted up and crash into one of the mirrors. That would be bad. And because of that, we have some wind speed limits above which we need to either restrict or close down the observations. But how does this actually work? Who can observe here? Well, astronomers from any country in the world can observe here, not just from countries belonging to ESO. But to observe here, they need to apply. There are a couple of periods during the year, when they have to send their observation proposals. And they need to be very detailed into what they want to observe, what is the scientific reason behind this, have this object been observed with other telescopes before or not, how far away the moon needs to be so it doesn't interfere with the quality of the observations, etc., etc. And a committee will decide to who they give time based only on the scientific merit of the proposal. And this is highly demanding. We receive here over 7 times more proposals than we actually have time to assign. So what's happened once you get your proposal accepted? Well, in that case, there are 2 observation modes. There is the visitor mode. In the visitor mode, you travel here, you are sit here on the chair, and you are supervising the observations. But you also have the service mode. In the service mode, you do not get to travel. You give the instruction to an astronomer from the ESO staff, and they handle the observations for you. Most of the observations in this observatory are through the service mode. And once the observations have been taken, they are private for the astronomer that sent the proposal for about a year. After that, everything is made public. So any astronomer can go to the ESO website and request the data. Of course, usually what you would do, you will send an email to the astronomer that sent the proposal and inform them that you want to use the data that they collected and what you want to do with them. And sometimes they will be very interested in what you're doing and maybe request for being a part of your investigation. You have to remember, astronomy is for the most part a very collaborative science. There are very little to none works done by single persons. Okay, we have talked a little bit about the process to observe here, but what are the results of these scientific observations? What are the top achievements made not only with Paranal, but all the observatories of ESO? And to show you that, we have a video with our top 10 discoveries. Can we show it, Farid?
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at Lucia was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, well, those were the top 10 discoveries made with the ESO telescopes and the scientific stuff behind them. But we have an extra result, a bit of a bonus track. A team of astronomers captured the first image of a supermassive black hole. Please take a look at the video. So, the Event Horizon Telescope, an array of 8 ground-based telescopes distributed throughout the planet, coordinated by an international collaboration, achieved the first direct visual evidence of a supermassive black hole and its shadow. This image reveals the black hole at the center of Messier 87, a massive galaxy in the nearby Virgo galaxy cluster. This black hole is 55 million light-years away from the Earth and has a mass of 6.5 billion times that of the Sun. A very impressive image of the black hole. Okay, we're going to continue with the tour. And I would like to mention to everybody that we have in-person tours at Paranal Observatory every Saturday, one at 10 a.m. and other one at 2 p.m. And we also have tours at La Silla Observatory as well. These tours, they are completely free, but you need to sign up in a website beforehand, and also you need to get to the observatory in your own vehicles. And there you will see more or less the same that we have been showing you here, but it's one thing that we can show you in the virtual tour that we cannot show you in the in-person tours. And this is the view of the night sky from the main platform of Paranal Observatory. We can do this with the magic of this virtual tour. So here we can see this beautiful night sky. It's not completely night. We can see a bit of light from the sunset over here. And let's start to see what we can find in this night sky. So over here we have one of the most recognizable constellations, Orion, the Hunter. This is a constellation that is visible both from the southern and northern hemisphere. And in the Greek mythology, Orion was the hunter. You have here the Orion's belt, his sword, and since this image is taken in the southern hemisphere, we see it upside down. Now, in the version of the story that I know, Orion was the best hunter there was, but he managed to anger Artemis, the goddess of the hunters. So Orion tried to hunt a deer that was sacred for Artemis, so she got very angry at that. So she decided to put Orion in the sky, where he will have to fight every animal that he has ever hunted. And that is why Orion is very close to the bull, the scorpion, Leo, but he also has his hunting dogs near him. Over here we have Sirio, Canis Majoris, part of the constellation of Canis Majoris, the brightest star of that constellation, and that is one of the dogs that accompanies Orion. And over here we have Taurus, the bull. Now, over here we have Orion's Bell, or as known in the southern hemisphere in Chile and some other countries as the Three Marys. And here, this is Orion Nebula, an area of star formation. And of course, in Orion we have Betelgeuse, which sometimes gives to talk about because it has been changing its brightness a little bit, and people expect that it will explode as a supernova somewhere in the next 100 of years. So whenever its brightness changes, it's always interesting. Now, over here we have the Pleiades, a very beautiful open star cluster. And if we look to this other side, now we can see some things that can only be visible from the southern hemisphere. So the main two are these foggy things over here. So these are the Magellanic Clouds. We have the big Magellanic Clouds and the small one. So these are satellite galaxies of our Milky Way. And you can actually use them to try to find the south direction. So unlike in the northern hemisphere, there is no bright polar star in the southern hemisphere. But one thing that you can do is you can take the two Magellanic Clouds and use them to build a triangle. In the point that you will need to fill, that is the southern celestial pole, and right below the southern cardinal direction. There is another way of getting the south direction using the Southern Cross. So the Southern Cross constellation is this one over here, the smallest of the constellations. And what you need to do is you take the bigger stick of the cross and extend it 1, 2, 3. Some people say 2.5, some people say 4 times, and you get to the same point as before. And that way you can find the southern direction. And here we can also see Alpha and Beta Centauri from the Centaurus constellation. And we can see this area where we see some black spots and some brighter spots. This is the spiral arm of the Milky Way or galaxy. And in the cosmovision that the natives of this area has, the natives of the Andes, the Milky Way was a river where animals will come to drink water. So for example, we have over here a llama. So we have here the neck of the llama, we have here his nose, one eye, the ears, and depending on the time of the year, you can also see part of the body of the llama. And we also have a bird and some other animals as well. And with that, we're going to conclude our visit to this beautiful night sky, and we are going to go back to the day. Now, we're going to head towards our next stop, and that is the base camp. So we're going to go down, and here we can see the base camp. This is like a mini city in itself. Here you have everything you need for the observatory to work in a correct way. So you have workshops where we build pieces to repair the telescopes or to build new instruments. We have the buildings where we do the recording process. But we also have other things like an infirmary. We have a gym. We have places where people stay and live. The observatory also has its own power plant. When this was first built, there was a power plant here to give electricity to the observatory. And later, the observatory was connected to the electricity grid of Chile, and the power plant was left as a backup. And the latest development in that front is that a solar plant for the observatory was built. So now it's more renewable energy. But our next stop is this place over here, this so-called residencia, which people sometimes call the hotel of the observatory. This is the place where the astronomers sleep, and it looks like we're going underground, but this building is actually built using the side of the mountain, and this building wins some architectural prizes. But before we go inside, let's take a look outside, and here you have this beautiful desert landscape that could be a little monotonous. It's more or less the same, different degrees of the same colors. There is very little green. But once inside, we are faced with this very lush tropical garden. Okay, so why do we have this here? And also, why do we have a pool here? Well, this is the driest desert in the world, and the dry air is not that good for people and for the skin and for breathing. So the pool here allows to have an environment with a higher humidity. And this is why also we have this beautiful garden over here, because we have an environment that is good for these plants to grow here. And having some green to look at is good for your mental health. Now, at the center over here, we have a curtain, but the purpose of this curtain is unlike the curtain that one usually have at his house. That curtains are to block the sunlight for coming inside. This one, the main purpose is that when we extend this, we can turn on the lights inside this building and prevent this light for going outside. So that way we don't disturb the scientific observations. Now, this building has 108 rooms over here. This is the reception, very similar to the reception of any normal hotel, but only the astronomer can stay here. It's not open for the regular public. Over here we have the cafeteria where people can eat breakfast, lunch, and dinner. There is a library, a music room, a game room. People stay here for several days. They work in shifts, so they need everything to have a normal life and not go crazy. Okay, and we are getting close to the end of today's tour. So let's see if we have any more questions or any more comments.
Hello, Hector. Well, I have been looking, but no, we don't have additional questions about this tour. Just the people looking at your nice presentation. Maybe maybe we can tell a little bit about what is necessary to do to book a reservation, or how much time in advance, and what basically is possible to see in the observatory if you go in person. Can you tell us a little bit?
Yes, so as I originally tell you, this is completely free. You need to register in a website. Farid, can you tell me the exact website? Is
Yeah, I was just asking if what is the usual process to visit the Paranal
yeah.
Observatory and some requirements. So, for example, how long is from the closest city, How long is the
Yeah, so
tour? This kind of logistics.
the closest major city to the observatory is Antofagasta. And for some people, you could actually like take a look at the uh, tours that people in the city offer, because they offer tours where they take you to different places and also to the observatory. But something more simpler that you can do if you are traveling there and visit there is to just rent a car and drive from there to the observatory. It's 130 kilometers south of the city, so about an hour and a half, maybe 2 hours, so you have some time to not drive very fast. You need to get with your own car. That is absolutely necessary. And you have to register in the website. There is some restriction about age limits. No kids below, I think it was 3 years. You can correct me if I'm wrong, Farid. And
Say again, Hector. I didn't hear you.
there are limits on the age of for kids, right?
Yeah, 4 years old.
4 years old. Okay, so that's the limit of age. And the tour start 1 at 10 a.m. You have to arrive a bit earlier than that, about 20 minutes to half an hour earlier, so the guys there can check that you were registered correctly in the website and that everything is in order. And then you will go inside the residential where we are right now. You will go into the main platform inside one of the telescopes. You will also go inside the control room, and you will have some time to take pictures in some of these places. In not all of them. And as I mentioned, it's completely free. One tour at 10 a.m., another tour at 2 p.m. You can also do tours at La Silla Observatory. I don't know the details for La Silla as well, but you should register on the website a couple of weeks in advance, because depending on the time of the year, this could be completely booked. And once the books are completely full, we don't allow extra people to go inside. So if you're going to travel to Chile and you intend to go to this area, to the north of Chile, when you can also go to other nice places like San Pedro de Atacama, for example, and you decide to stop by the observatory, book your visit a couple of weeks in advance. And I hope that gives anybody the idea of how to do this.
Yeah, thank you. Thank you very much, Hector. So, well, I think we are now in condition to finish this experience. Thank you so much. So I give you time for finish.
Okay, so I would also like to remind everybody that you can always go to the ESO website, www.eso.org, and there you can find hundreds of photographs and videos that you can download and use for whatever purpose you want to use. You can also find the spiritual tour that you can move through at your speed and see all the different things that there are as well. And in the name of ESO, I would like to thank you for being a part of this virtual tour. We are doing virtual tours every Saturday. We are alternating between La Silla Observatory and Paranal Observatory, and also between English and between Spanish. So please keep an eye on our social networks to see uh, when is the next tour and in which language is going to be and of which observatory. And please also share this with any friends or family that you know that might find this content interesting. And I believe we also have a survey for the people to fill. Uh, do we have
Yes,
this?
Hector, the survey is now in the comment box in Facebook and YouTube.
So you can leave your feedback there so we can improve on this experience. And on behalf of ISO, I say goodbye, and I hope that everybody has a very nice days and a very nice 2025. So goodbye to everybody.
Thank you. Goodbye.